Then we are going to move on to Dr. Anderw Jordan, who is doing a talk on observational evidence for dielectric breakdown weathering on the moon. Dr. Jordan, feel free to take over whenever you're ready.
All right, can you hear me?
Yes, I can hear you.
And can you see my slide?
Mm-hmm.
Okay, great, thanks. So this is work that's been supported by LRO Crater and Survey's leader team. And that's an old picture of me, but I chose it because it's from a lunar science forum many years ago. And I really liked the lanyard back then. We've had some great talks on space weathering, and the current view is that mainly micrometeoroids and the solar wind dominate space weathering, and it's a bit of a discussion as to which one's more important. For the past few years, I've been arguing that another space weathering process is going on the moon called dielectric breakdown. And what happens is during large solar storms like coronal mass ejections or solar flares, these magnetic events accelerate particles to high energies. These are called solar energetic particles, or SEPs. And these SEPs can cause deep dielectric charging in cold soil on the moon. So by cold, I mean less than about 100 or so Kelvin. And that's in permanently shadowed regions on the night side of the moon. And SEPs don't follow lines of sight from the sun like the solar wind does, or like an electromagnetic radiation. Some of them have really large gyro radii, so they can hit the night side of the moon. They scatter off the magnetic irregularities in the magnetic field, in the heliospheric magnetic field. So observations from Crater, from Lunar Prospector have shown that SEPs can hit the night side of the moon. And during really large events, they can charge the soil to the point where the electric field in the top millimeter or so causes dielectric breakdown, or you can think of it as sparking or lunar lightning, I guess, but just really small. And you get rapid melting, vaporization. And in our 2019 paper, we predicted that dielectric breakdown weathering should be comparable to micrometeoroid weathering. And in that paper, we predicted a latitude profile for the energy flux of breakdown weathering into the lunar soil in terms of joules per meter squared per year. You can see it varies, it increases by about 20% from the equator to the pole. And in that paper, we used the Grunewald 1985 mass flux and Santala's velocity to calculate an energy flux for the micrometeoroids. And since then, I've combined that with a latitudinal distribution that Gallant et al. Found. So that's a cosine of latitude function that decreases by 10% from the equator to the pole. And so you can see the micrometeoroids seem to be contributing more weathering, more melting and vaporizing than does breakdown on a global scale. But because both of these processes are melting and vaporizing, it seems reasonable to add the two together to get a net profile for this. And what you see is here in the bottom plot, the weathering profile is roughly constant from the equator up to about 40 or so degrees. And then it starts rolling over and becomes more and more like the cosine of latitude at higher latitudes. And I'm not showing the solar wind on this because its energy flux is a few orders of magnitude higher than this. So you wouldn't see any of those variations. So now I'm going to compare this to the reflectance profile of the Maria. And I'm focusing on the Maria because the latitudinal trends are clear there. They've been studied in more detail. Hemingway et al. In 2015 did one of the studies, and I'm showing data from that paper. On the left is the Maria reflectance at 750 nanometers, and on the right is the reflectance at 1064 nanometers. I'm showing the 1 sigma there. And if you just take that weathering profile from the previous page, the bottom plot there, and just fit it to the data, I just fit it at, or set it equal to the data at the equator and at 60 degrees latitude using the equation on the upper left-hand corner. I just take breakdown plus micrometeoroid energy flux, multiply it by a negative constant, and that just flips the sign, and then add another constant. And then you get the fits that you see here. And the reflectance data show a similar trend as the modeled reflectance, where both of them are flat out to about 40, latitude 40 degrees, and then it starts increasing rapidly at higher latitudes. Now, if the solar wind were dominating weathering, you'd expect the reflectance data to follow a cosine of latitude trend. And that's what this dotted line is here. And the cosine of latitude trend does not seem to fit the data. And so it seems like the Maria reflectance can be best explained by this combination of dielectric breakdown and micrometeoroid weathering. And we've been talking quite a bit about swirls, and I really enjoyed the previous two talks. It's given me a bit to think about. Here I'm just going to talk a little bit about Reiner Gamma, which I did vote for. It has a magnetic field strength of about 20 nanotesla at an altitude of 30 kilometers. Now this is fairly weak if you're an SEP particle. So most SEPs can penetrate right to the surface. So all SEP protons and the energetic electrons have energies, gyroradii, that are large enough to make it to the surface. I'm just using a simple gyroradius argument. Lower energy SEP electrons, so on the order of 10 keV and lower, they can be reflected or shielded out by the magnetic field. So we'd expect breakdown weathering to be reduced in a swirl. And just for some context, the solar wind is reduced by about 80% at the surface by this magnetic field. So we'd expect breakdown weathering to be reduced by quite a bit less than that, because we're talking about more energetic particles. So let's go back to the data. So there again, you see the reflectance of the Maria with latitude, and then that star shows where Reiner Gamma is at a reflectance of about 0.15. And then there's the fit of the model to the reflectance. And then if I decrease breakdown weathering by just 3%, that's more than enough to explain the brightness of Reiner Gamma. And 3% is, as it should be, a whole lot less than 80% shielding that you get of solar wind. So just reducing breakdown weathering by a little bit, which is what you'd expect, given how energetic these particles are, seems like you can explain the brightness of Reiner Gamma. Now, some of you are probably thinking, well, how can you argue that the solar wind doesn't cause any weathering? There's been about 60 years worth of experiments saying that it does. And I can't go into detail about this. This is a paper that's in preparation, but I wanted to make one point about that. In order to keep laboratory timescales reasonable, these studies have to use really high fluences of particles. So the ones that I've reviewed are all 10 to the 14 to 10 to the 20. I think I've even seen one up to 10 to the 21 charged particles per centimeter squared. But dielectric breakdown in most solid dielectrics, which includes things like lunar soil and simulant, only needs 10 to the 10 charged particles per centimeter squared. So these experiments are exceeding the threshold needed for dielectric breakdown by 4 to 10 orders of magnitude. And the solar wind can't cause this kind of charging because it's hitting the day side of the moon, where the soil is a lot warmer, so the electrical conductivity is a lot higher, and it can dissipate that charging. So it seems like these experiments might actually be not so much a simulation of solar wind weathering, but they might actually be a better proxy for breakdown weathering. But stay tuned, hopefully I'll be able to talk more about that at a later date. So to summarize, the Maria reflectance shows a fairly level trend from about 0 from the equator to about 40 degrees, and then it increases rapidly. And it doesn't seem to follow a cosine of latitude trend. So it doesn't seem that the solar wind dominates. Whereas the breakdown plus micrometeoroid trend, based on the work that we did in 2019, does have that region of level weathering or constant weathering from the equator to about 40 degrees. And then it increases rapidly after this. So I'm proposing that maybe it's micrometeoroids and dielectric breakdown that are dominating weathering in the Maria, and the solar wind might play a minor role. So thank you, and I'll take any questions. You can also email me questions if you want.
Okay, that is fascinating. I'm going to take a host prerogative, and I'm going to ask you a question. So I see that nice plot of yours, and is this lunar specific, or can you apply it to Mercury?
Oh,
You've got another
man,
2 minutes.
Yeah. Mercury does have a magnetic field. So this might play a role near the poles, near the cusp regions, where these SCP particles can get in. I don't know about lower latitudes.
So if someone were to send you, for example, flux to the surface as a function of time for Mercury, could you say where this dielectric breakdown would be probable, or a process to consider, and where it would not be effective?
Yeah, definitely.
Okay, so I'll be in touch then.
Sounds good.
Okay, so we do have another question. Let's see, what kind of subsurface geologic feature would it take to explain the magnetic field lines? And how deep would they have to be buried?
Oh, that's above my pay grade. I'm a particle guy. I'm not a geophysics guy.
Okay, fair enough.